Maintaining heavy transport corridors in hot, arid regions subjects infrastructure to intense thermal stress and relentless heavy axle loads. The visual evidence of this fatigue is obvious. Severe alligator cracking, deep rutting, and degraded asphalt shoulders define these failing segments. These surface failures demonstrate that the underlying pavement layers have lost the capacity to bear traffic loads. High ambient temperatures and moisture variations accelerate this underlying degradation, forcing authorities into a continuous, expensive cycle of surface patching that never addresses the root cause. This leaves major agent highways characterized by long stretches of mismatched repair work and systemic wear. Milling and repaving the asphalt surface alone is a temporary financial drain. True rehabilitation requires rebuilding the foundational strength of the base layers beneath it. The traditional method for base repair is dig and replace, a logistically heavy process that requires mass excavation and export of the exhausted road base. This approach incurs heavy environmental and financial costs. It demands fleets of heavy transport, long corridor closures, and complete reliance on importing massive volumes of virgin aggregate. The engineered alternative relies on in-situ rehabilitation, utilizing techniques like cold-in-place recycling and full-depth reclamation to rebuild the base using the existing road materials. Within this process, MASTER CTS developed the MASTER FLOK Road Rehabilitation and Soil Stabilization System. MASTER FLOK is not a standalone binder. It is an additive designed specifically for use with Portland cement. The system acts as a structural modifier, improving the performance of treated soils, granular materials, and recycled pavement layers during the mixing phase and throughout the pavement service life. By modifying the behavior of the cement matrix, MASTER FLOK enables engineers to convert weak, deteriorated in-situ material into a highly resilient structural base layer, entirely eliminating the need for mass excavation. The execution of MASTER FLOK follows a standardized 9-step sequence. The operation begins with rigorous field assessment. Engineers evaluate the exact pavement distress to define the intervention before machinery is deployed. Step 2 initiates rehabilitation with the distribution of the binder over the roadway. The distributed material is applied as a dry matrix. It consists of specifically proportioned Portland cement combined with the MASTER FLOK modifier. In the field, specialized distribution trucks lay down this white powder matrix in a highly controlled path directly ahead of the recycling zone. This uniform distribution is an absolute prerequisite. The structural integrity of the final road base depends on an even, consistent application of this modified matrix. Steps 3 and 4 introduce water integration and active heavy machine operation. A dedicated water tanker is physically tethered to the heavy recycler. This configuration ensures exact moisture parameters are met and maintained throughout the mixing process. Beneath the recycler, a heavy milling drum cuts deep into the pavement, pulverizing the existing asphalt and exhausted base material in situ. Simultaneously, this freshly pulverized material is chemically blended with the pre-laid cement and MASTER FLOK matrix. During this active mixing phase, MASTER FLOK provides a critical mechanical advantage. It improves workability and optimizes the material's tolerance to moisture variations.
In a single, continuous forward pass, the recycler processes the failing roadway and ejects a homogeneous, chemically modified fresh base, ready for immediate shaping. Immediately after mixing, the new base material is highly aerated. It must undergo structured consolidation before the cement matrix begins its curing cycle. Step 5 introduces initial densification. A smooth drum compactor makes the primary passes, applying heavy force to drive out deep air voids from the milled layer. Step 6 transitions to grading and precise profile control. A muter grader actively cuts and shapes the densified material, correcting the geometry to meet strict elevation and crossfall engineering requirements. Step 7 applies secondary consolidation to lock in this newly graded profile. A tandem roller systematically works across the entire lane width, achieving the precise target density required for structural stability. Step 8 is the final surface sealing phase. A heavy pneumatic tire roller kneads the top surface. This action closes remaining microvoids and tightens the layer, preventing future water ingress. This sequential four-machine compaction choreography completes the active physical workflow, locking the chemically modified matrix into its final engineered geometry. With the mechanical operations finished, the focus shifts to the invisible chemical kinetics occurring within the newly compacted base. Standard cement-treated bases set rapidly and rigidly, generating high shrinkage stresses that make the layer susceptible to cracking and subsequent moisture damage. This timeline illustrates MASTER FLOK's primary kinetic shift. It significantly extends the final setting time, expanding the compaction window from approximately 4 hours to 8.5 hours, which effectively neutralizes severe shrinkage stresses. A field-proven recipe logic demonstrates the efficiency of this system, blending 100% existing granular material with 6% M400 cement, just 0.6% MASTER FLOK, and 1.5% water. The resulting structural capacity is massive. The stabilized base achieves extremely high stiffness, reaching an elastic modulus, or EDAD value, of up to 2,900 megapascals. By combining a forgiving extended working window with exceptionally high ultimate stiffness, the system directly addresses the traditional fragility and cracking failures inherent to standard cement treatments. Achieving an elastic modulus of 2,900 megapascals significantly changes standard pavement design logic. This cross-section shows the first major optimization. The stiffness of the treated layer permits the complete elimination of the traditional granular subbase. Furthermore, this structural efficiency allows for up to a 50% reduction in the required thickness of the final asphalt surface course. These material savings translate directly into operational velocity. Daily production rates jump from between 3 and 500 linear meters under traditional methods to between 12 and 1,500 meters per day. By bypassing excavation and eliminating demolition export, this method yields a carbon reduction of up to 46 metric tons of CO2 per kilometer. The physical result is a fully rehabilitated, highly controlled stabilized base course, ready to support years of heavy regional traffic. MASTER FLOK transforms regional road rehabilitation into a highly controlled, environmentally efficient, in-situ engineering solution.